Good evening, dear listeners. As you settle into the quietness of this moment, prepare to embark on a journey that will challenge everything you thought you knew about reality itself. Tonight, we're going to explore one of the most profound and mind-bending concepts in modern physics, the multiverse. The idea that our universe, vast and ancient as it is, might be just one bubble in an infinite cosmic foam, that every choice, every quantum event, every possible outcome might exist somewhere, in some reality, playing out in ways we can scarcely imagine. Before we begin this extraordinary voyage into the nature of existence itself, I invite you to like this video and subscribe to the channel. Your support gives me the motivation to continue bringing you these deep explorations of our magnificent cosmos. And now, let's drift into the dream of exploring the vast multiverse with AstroMind. The question that changed everything. Imagine standing on the shore of a vast ocean. The waves lap at your feet, and you can see the horizon stretching endlessly before you. For most of human history, we thought our universe was like that ocean, vast and complete, containing everything that exists. But what if that ocean is just one drop of water in an infinite sea? What if our entire universe, with its trillions of galaxies, its billions of years of history, its countless stars and worlds, is just one room in an infinitely vast mansion? This is the question at the heart of multiverse theory. And it's not science fiction. It's not wild speculation dreamed up by philosophers with too much time on their hands. The multiverse emerges, surprisingly and somewhat reluctantly, from the very mathematics that physicists use to describe our reality. It comes from equations that have been tested and verified countless times. It arises from theories that successfully predict the behavior of particles, the evolution of the cosmos, and the fabric of space-time itself. The strange thing about the multiverse is that many physicists who work on these theories never set out to find other universes. They were trying to understand this one. They were solving equations, testing theories, and following the mathematics wherever it led. And where it led, again and again, was to the unavoidable conclusion that our universe might not be alone. That reality might be far larger, stranger, and more wondrous than we ever dared to imagine. The birth of a revolutionary idea. The story of multiverse theory doesn't begin with a single eureka moment. It emerges gradually from several different areas of physics, each independently pointing toward the same unsettling conclusion. Like blind men describing different parts of an elephant, different branches of physics began describing what appeared to be different aspects of a much larger reality. But if we're looking for a place to start, we might choose a seemingly unrelated question that puzzled physicists in the early 20th century. Why does quantum mechanics work the way it does? Why do particles exist in multiple states at once until they're measured? Why does the act of observation seem to collapse infinite possibilities into a single outcome? In the 1920s and 30s, as quantum mechanics was being developed, physicists noticed something deeply strange. When you're not looking at a quantum particle, like an electron, it doesn't have a definite position. Instead, it exists in what's called a superposition, a combination of all possible positions at once. The mathematics describes this beautifully with something called a wave function, an equation that gives you the probability of finding the particle at any given location. But here's where things get weird. The moment you measure the particle's position, the wave function collapses. Suddenly, the particle is in one specific place, and all the other possibilities vanish. Poof, gone, as if they never existed. This seemed deeply unsatisfying to many physicists. The equations of quantum mechanics don't say anything about this collapse. They describe smooth, deterministic evolution of the wave function over time. Then, suddenly, when a measurement happens, you have to abandon those equations and introduce a completely different process, one that's random and instantaneous. It's like having a beautiful, elegant theory that works perfectly, except you have to break it every time you look at it. Niels Bohr and his colleagues in Copenhagen decided to accept this strange state of affairs. They developed what became known as the Copenhagen interpretation, which essentially said, yes, measurement is special. Yes, observation collapses the wave function. That's just how quantum mechanics works. Don't worry too much about what's really happening. The theory makes predictions. Those predictions match experiments, and that's what matters. But not everyone was satisfied with this answer. Hugh Everett and the Many Worlds. In 1957, a graduate student at Princeton University named Hugh Everett III was thinking about these problems. Everett was brilliant, unconventional, and perhaps a bit too clever for his own good. His thesis advisor was John Wheeler, one of the giants of 20th century physics. And Everett had a radical idea. What if, Everett asked, the wave function never collapses? What if every possible outcome of a quantum measurement actually happens? Not as mere possibilities, but as real, physical events in a vast ensemble of parallel universes? Think about Schrödinger's famous cat for a moment. In the traditional thought experiment, a cat is placed in a sealed box with a quantum device that has a 50% chance of releasing poison. According to quantum mechanics, before you open the box, the cat is in a superposition of being both alive and dead. Only when you look does the wave function collapse, and the cat becomes definitely alive or definitely dead. Everett's interpretation removes the collapse entirely. When you open the box, the universe splits. In one universe, you find the cat alive. In another universe, equally real, you find the cat dead. Both versions of you exist in separate realities, observing different outcomes, and crucially, neither version knows about the other. The universes branch apart and can never interact again. This sounds insane, and Everett's contemporaries certainly thought so. When Wheeler presented Everett's ideas to Niels Bohr in Copenhagen, Bohr was dismissive. He couldn't see any reason to take seriously the notion of splitting universes. It seemed like unnecessary metaphysical baggage. Why postulate an infinity of unobservable universes when you could just accept that measurements collapse wave functions? Everett tried to defend his ideas, but the physics establishment wasn't ready to listen. Frustrated, he left academia entirely. He went to work for the Pentagon, doing classified research on nuclear strategy and game theory. He made a lot of money, developed a drinking problem, and died in 1982 at the age of 51, never knowing that his radical ideas would eventually become one of the most discussed interpretations of quantum mechanics. Because something strange happened in the years after Everett abandoned physics. As more physicists studied quantum mechanics deeply, especially in the context of quantum cosmology, trying to apply quantum mechanics to the universe as a whole, they kept running into the same problems that Everett had identified. And slowly, reluctantly, some began to think that maybe, just maybe, he had been onto something. The mechanics of branching. To understand how the many worlds interpretation actually works, we need to think carefully about what happens during a quantum measurement. Let's start with something simple, a quantum coin flip. Imagine you have a device that puts an electron into a superposition of spinning clockwise and counterclockwise. Before you measure it, the electron is in both states at once. That's not a metaphor or a limitation of our knowledge. According to quantum mechanics, the electron genuinely has no definite spin direction until it's measured. Now you measure the spin. In the Copenhagen interpretation, the wave function collapses, and you randomly get one result or the other. In Everett's interpretation, no collapse happens. Instead, the interaction between your measuring device and the electron causes the wave function of the entire system, including you, to evolve into a superposition of two distinct outcomes. In one branch of the wave function, you measure spin-up. Your brain records that measurement. Your memory encodes it. If you write it down, the paper records it. The photons bouncing off the paper record it. The entire universe around you becomes correlated with that measurement result. In another branch, equally real and equally physical, you measure spin down. Another version of you records that result, with all the same physical processes happening, just with the opposite outcome. Crucially, these two versions of you can't communicate. They exist in what physicists call different branches of the universal wave function. The branches have split, or more accurately, they've become decoherent. The quantum interference between them has become so small that for all practical purposes, they're separate realities. This happens not just for artificial laboratory measurements, but constantly, everywhere, at every moment. Every quantum interaction that has multiple possible outcomes creates new branches. An atom absorbs a photon or doesn't. A particle decays or doesn't. A cosmic ray strikes an air molecule in Earth's atmosphere at one angle or another. Each event multiplies the number of branches. How many branches are there? That's a question that doesn't have a simple answer. Some versions of the many worlds interpretation suggest the number of branches is infinite, continuously increasing at every moment. Others suggest it might be enormous but finite, depending on the details of quantum mechanics and the history of the universe. But either way, the number is staggeringly large, beyond human comprehension. And here's something that often gets lost in popular discussions. You don't have any control over which branch you find yourself in. From your subjective perspective, outcomes still appear random, just as they do in the Copenhagen interpretation. The difference is that instead of possibilities collapsing to nothing, they continue to exist in other branches. Every possible outcome happens, but you only experience one. Level 1, the infinite universe next door. But the quantum multiverse, strange as it is, isn't the only kind of multiverse that physics predicts. There's another type, perhaps even more mind-bending, that arises from cosmology rather than quantum mechanics. This is what cosmologist Max Tegmark calls the Level 1 multiverse, and it's based on a simple observation. The universe might be infinite. We can only see a finite portion of the universe. Light has had only about 13.8 billion years to reach us since the Big Bang, and space has been expanding all that time. This gives us an observable universe with a radius of about 46 billion light-years. Everything within this sphere, this cosmic horizon, is potentially visible to us. Everything beyond it is not, because light from those regions hasn't had time to reach us yet. But here's the thing, there's no reason to think the universe stops at our horizon. The universe probably continues beyond what we can see. It might even continue forever. If the universe is infinite in extent, and if the Big Bang started everywhere at once, then beyond our cosmic horizon, there are other regions of space, other observable volumes, other universes, in a sense, completely isolated from ours, not by any barrier, but simply by distance and time. Now, here's where it gets interesting. If the universe is truly infinite, and if the laws of physics are the same everywhere, which all our observations suggest they are, then the number of possible arrangements of matter and energy, while enormous, is finite. There are only so many ways you can arrange the particles in a region the size of our observable universe. This leads to a stunning conclusion. If the universe is infinite, then every possible arrangement that can happen must happen somewhere, and not just once, an infinite number of times. Think about what this means. Right now, you're reading these words, but in another region of space, impossibly far away, beyond countless galaxies and cosmic horizons, there's another Earth. And on that Earth, there's another you, reading these exact words. Not a copy in the science fiction sense, not a doppelganger transported from another dimension, just another region of space where matter happens to be arranged in exactly the same way. In fact, there are infinitely many such regions, infinitely many yous, infinitely many Earths, infinitely many versions of human history playing out in exactly the same way. But there are also infinitely many versions playing out differently. Earths where you made different choices. Earths where history took different turns. Earths where the asteroid that killed the dinosaurs missed, or where humans never evolved, or where the laws of chemistry work slightly differently, allowing for completely different forms of life. This isn't speculation. It's a mathematical consequence of an infinite universe with finite arrangements. The physicist Max Tegmark has calculated roughly how far you'd need to travel to find another version of yourself. The answer? About 10 to the power of 10 to the power of 28 meters. That's a 1 followed by about 10 to the 28 zeros. The number is so large that writing it out would require more atoms than exist in the observable universe. So while these parallel regions exist, they're not practically reachable. The expansion of space ensures that we'll never meet our doppelgangers in this type of multiverse. They're causally disconnected from us, forever beyond any possible interaction or observation. Level 2, bubble universes and eternal inflation. Now we come to an even stranger type of multiverse, one that arises from our best theories of the Big Bang itself. This is the Level 2 multiverse, sometimes called the bubble universe multiverse or the inflationary multiverse. To understand this, we need to talk about cosmic inflation. In the early 1980s, physicist Alan Guth proposed a solution to several puzzling features of the Big Bang theory. Why is the universe so uniform? Why do distant regions that couldn't have ever been in contact look so similar? Why is the universe so flat, balanced on a knife edge between expanding forever and collapsing back? Guth's answer was inflation, a period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang. During inflation, a region of space smaller than an atom expanded to astronomical size faster than light could cross it. This would explain the uniformity, because all the different regions we see today came from a tiny patch that had time to reach equilibrium before inflation began. It would explain the flatness, because inflation stretches space smooth, like blowing up a wrinkled balloon. The evidence for inflation has grown stronger over the years. Observations of the cosmic microwave background, the afterglow of the Big Bang, show exactly the pattern of tiny fluctuations that inflation predicts. Most cosmologists now accept that something like inflation probably happened. But here's where it gets interesting. The simplest models of inflation suggest that it doesn't happen everywhere at once. Instead, inflation is driven by a quantum field called the inflaton field. In some regions of space, this field reaches the right conditions to stop inflating, and a normal universe like ours emerges. But in other regions, inflation continues. This leads to what physicist Andre Linde calls eternal inflation. Once inflation starts, it never completely stops. It keeps creating new regions of space. Some regions exit inflation and form bubble universes like ours, with galaxies and stars and planets. But between these bubbles, space continues to inflate exponentially, forever generating new volume, new regions, new opportunities for more bubbles to form. This creates a vast cosmic structure. Our universe is one bubble in an eternally inflating foam. Other bubbles are constantly forming, each creating its own universe with its own history, its own galaxies, its own potential for life. And the inflation between the bubbles expands so fast that no bubble can ever make contact with another. We're isolated in our bubble universe, surrounded by an infinite expanse of inflating space, with countless other bubble universes scattered throughout it, all causally disconnected from each other and from us. But here's where it gets even stranger. In different bubbles, the laws of physics might be different. Not completely different. They all emerge from the same underlying theory, but different in the details. The strength of gravity might vary. The mass of the electron might be different. The number of spatial dimensions that aren't curled up might change. This brings us to string theory, and what's called the string landscape. The string landscape, 10 to the 500 universes. String theory is one of the most ambitious projects in theoretical physics. The idea is beautiful. What if the fundamental constituents of reality aren't point particles, but tiny, vibrating strings? Different vibration patterns would correspond to different particles. A string vibrating one way is an electron. Vibrating another way, it's a photon or a quark. To make the mathematics work, string theory requires extra dimensions of space beyond the 3 we experience. The most common versions need 10 or 11 dimensions total. The extra dimensions are thought to be curled up, compactified into tiny shapes, too small to detect directly. But here's the problem. There are many, many ways to curl up those extra dimensions. Each different geometry gives you a different version of physics in the remaining dimensions, the ones we can see. Different particle masses, different force strengths, different values for what we call the constants of nature. How many different ways? For a long time, string theorists hoped there might be just one, a unique solution that would give us the physics we observe. But as they explored the mathematics more deeply, they discovered something dismaying. The number of possible solutions, the number of different ways to compactify the extra dimensions, is enormous. Current estimates suggest something like 10 to the power of 500 distinct possibilities. That's a 1 followed by 500 zeros. More possible universes than atoms in our observable universe, raised to some ridiculous power. This is called the string landscape. Each point in this landscape corresponds to a different way of curling up the extra dimensions, and thus to a different set of physical laws. And if eternal inflation is correct, then all of these possibilities might be realized somewhere in the greater multiverse. Different bubble universes would crystallize with different vacuum states, different compactifications, different laws of physics. In some bubbles, gravity might be much stronger, causing stars to burn out in millions of years instead of billions. In others, the electromagnetic force might be different, preventing atoms from forming. In some, there might be extra fundamental forces we've never encountered. In others, fewer forces or different particles entirely. Most of these bubble universes would be sterile, unable to support complexity or life. Stars might not form, or atoms might be unstable, or matter might not clump together into galaxies. But in a tiny fraction of bubbles, the conditions would be just right, and we find ourselves, necessarily, in one of those rare bubbles, because those are the only ones where observers can exist to wonder about such things. This is called the anthropic principle, not as an explanation for why the constants of nature have the values they do, but as a selection effect. In a multiverse with vastly varying physics, we can only observe universes compatible with our existence. It's not surprising that we find ourselves in a universe with just the right properties for stars, planets, and life, because that's the only kind of universe we could find ourselves in. Some physicists love this idea. It explains, they say, why certain numbers in physics seem so finely tuned. Why is the cosmological constant, the energy density of empty space, so absurdly small? Because in most bubble universes, it's much larger. But those universes expand so fast that galaxies never form. We live in a rare bubble where it's small enough for structure to develop. Other physicists hate it. They see it as giving up on finding a deeper explanation. Instead of explaining why the constants have their observed values, the multiverse simply says, all values exist somewhere, and we happen to be in a universe with these particular values. It trades explanation for enumeration, understanding for acceptance. The debate continues. But what's remarkable is that this isn't just philosophy. These ideas emerge from serious attempts to solve real problems in physics. String theory wasn't invented to create a multiverse. Inflation wasn't designed to generate bubble universes. These consequences emerged from the mathematics, whether physicists wanted them or not. Level 3. The quantum multiverse returns. Now we need to circle back to where we started, with Hugh Everett and the many worlds interpretation of quantum mechanics. Because Tegmark classifies this as a separate type of multiverse, Level 3, even though it's based on the same physics we discussed at the beginning, the quantum multiverse is different from the Level 1 and Level 2 multiverses in a crucial way. In those versions, the other universes are out there, somewhere in space. They're distant regions or separate bubbles, physically disconnected but existing in the same overall space-time. The quantum multiverse is different. The branches of the wave function don't exist in some other region of space. They're not out there beyond our cosmic horizon or in another inflation bubble. They exist here, superimposed on top of our reality, but decohered from it. There are other ways that the exact same piece of space-time could have evolved, given different quantum outcomes. This is subtle, and it's easy to get confused about it. You might think, if every quantum event causes the universe to branch, and quantum events are happening everywhere constantly, then doesn't the number of branches grow exponentially, faster and faster, until it's incomprehensibly huge? Yes, and the key word there is incomprehensibly. The number of branches in the quantum multiverse, if the many worlds interpretation is correct, is absolutely staggering. It grows with every quantum event, everywhere, every infinitesimal moment. The branching is continuous, relentless, and all-encompassing. But here's something important. The branches have different weights in quantum mechanics. Some branches carry more of what's called quantum measure than others. When you flip a fair quantum coin, The branches where you get heads and where you get tails have equal weight. But when you flip a biased quantum coin, the branches aren't equal. More of the quantum measure goes to the more likely outcome. This is how many worlds reproduces the probabilities of quantum mechanics. It's not that you're more likely to find yourself in one branch than another in some absolute sense. From your perspective before a measurement, you're going to experience some outcome with certainty. But the quantum measure on different branches determines what we call the probability of each outcome. This is one of the more subtle and controversial aspects of many worlds. How do you extract probabilities from a deterministic theory where every outcome happens? The answer involves the Born rule, the fundamental rule in quantum mechanics that tells you how to calculate probabilities from the wave function. Deriving the Born rule from the structure of many worlds is possible, but it requires some sophisticated mathematics and some assumptions about rational decision-making. Still, many physicists find this preferable to the alternative, accepting that measurement somehow causes a real physical collapse of the wave function, a process that's not described by the Schrödinger equation and that introduces fundamental randomness into physics. The many worlds interpretation says, the universe is deterministic. Every possibility happens. What appears to be randomness is just your subjective uncertainty about which branch you'll find yourself in. The wave function never collapses. It just keeps evolving, smoothly and deterministically, generating endless branches, all real, all physical, all described by the same elegant mathematics. Level 4. The mathematical universe. Now, we come to the strangest multiverse of all, the one that pushes the concept to its absolute logical extreme. This is Tegmark's Level 4 multiverse, and it's based on a philosophical idea more than a physical theory. The idea is this: what if mathematical structures don't just describe reality? What if they are reality? Think about it this way. Physicists describe the universe using mathematics. The Schrödinger equation tells us how quantum states evolve. Einstein's field equations tell us how matter and energy curve spacetime. The standard model of particle physics describes all the known fundamental particles and forces. But these equations are more than just descriptions. They make predictions. They tell us what will happen in situations no one has ever observed. And when we test those predictions, nature obeys. The mathematics isn't just a convenient language for talking about reality. It seems to capture something deep and essential about how reality works. Tegmark takes this one step further. He argues that a complete description of the universe would be a purely mathematical structure with no additional properties. If you could write down the perfect theory of everything, it would be just mathematics. There wouldn't be anything else to say. But if that's true, Tegmark asks, then why should our particular mathematical structure be the only one that exists? Why not all of them? In the Level 4 multiverse, every internally consistent mathematical structure exists as a physical universe, not as a description of a universe, but as a universe itself. A universe where space is four-dimensional instead of three, existing as physically as ours. A universe where matter obeys different equations, governed by different symmetries, following different mathematical rules. This is what Tegmark calls the mathematical universe hypothesis, and it leads to a multiverse that's not just larger than the others we've discussed. It's incomparably larger, infinitely larger, in a sense that makes the other infinities seem small. The Level 1 multiverse is infinite in extent but follows the same laws everywhere. The Level 2 multiverse has different laws in different bubbles, but they all come from the same underlying theory, like string theory. The Level 3 multiverse has all possible quantum histories, but they all obey quantum mechanics. The Level 4 multiverse includes all possible mathematical structures, universes without quantum mechanics, universes without space or time as we understand them, universes so different from ours that we couldn't even conceive of them, let alone live in them. Most physicists think this is going too far. Even those who accept the possibility of level 1 or 2 or 3 multiverses often balk at level 4. It seems too speculative, too untethered from observation, too much like philosophy masquerading as physics. But Tegmark argues that it's actually the most conservative possibility. If we accept that mathematical structures exist in some sense, and if we accept that our universe is described by a mathematical structure, then positing that only our particular structure exists requires an additional assumption. Why this one and not others? Level 4 removes that assumption and treats all mathematical structures equally. Whether you find this convincing or not probably depends on your philosophical inclinations. But it's worth noting that Tegmark isn't alone. Various philosophers and physicists have proposed similar ideas from different starting points, often converging on something like the Level 4 multiverse, the simulation hypothesis. Before we move on, we should mention one more multiverse idea that's captured public imagination: the simulation hypothesis. This is the notion that our universe might be a computer simulation running on some vastly advanced civilization's technology. The philosopher Nick Bostrom argued that at least one of three things must be true. Either civilizations tend to go extinct before developing the technology to run detailed simulations of conscious beings, or advanced civilizations choose not to run such simulations, or we are almost certainly living in a simulation right now. The reasoning is based on probabilities. If it's possible to run detailed simulations of conscious beings, and if advanced civilizations are interested in running such simulations, then the number of simulated conscious beings would vastly outnumber the real ones. And if that's the case, you should think it's more likely that you're simulated than real. This creates another kind of multiverse. If we're in a simulation, there might be many other simulations, each creating its own virtual universe. And the real universe running the simulations might itself be a simulation in some higher reality. Simulations all the way up, or perhaps more accurately, all the way down. The simulation hypothesis is hard to take seriously in a scientific sense because it doesn't make clear predictions. A sufficiently advanced simulation could be indistinguishable from reality. There's no test you could run that would definitively prove you're in a simulation, because the simulation could simply be programmed to give you any result the simulators want. But some physicists have suggested that imperfect simulations might show artifacts. If our universe is running on a finite grid, like the pixels on a screen but much, much finer, we might detect evidence of this discretization at small scales. Some have even proposed experiments to look for such effects, though nothing has been found so far. More philosophically, the simulation hypothesis raises questions about the nature of reality and consciousness. If you're conscious and you feel like your experiences are real, does it matter whether you're made of atoms or of bits in a computer? Is there even a meaningful difference? The problem of evidence. All of these multiverse ideas face a common challenge. How do you test them? Science is supposed to be empirical. You make a theory, derive predictions, test those predictions through observation or experiment. But the defining feature of most multiverse theories is that the other universes are unobservable. By definition, we can't see them, can't travel to them, can't interact with them in any way. So are multiverses even science? Or are they just metaphysics dressed up in mathematical clothing? This has been a major point of contention. Critics, like Paul Steinhardt and George Ellis, have argued that multiverse theories are inherently unscientific because they can't be falsified. If every possible outcome exists somewhere in the multiverse, then nothing can count as evidence against the theory. Anything we observe is compatible with a multiverse, because somewhere in that multiverse, a universe like ours must exist. Defenders of multiverse theories respond in several ways. First, they point out that the multiverses aren't hypotheses in themselves. They're predictions of other theories that do make testable predictions. Inflation makes predictions about the cosmic microwave background that can be tested. Quantum mechanics makes countless predictions that have been verified. String theory, while not yet experimentally confirmed, makes definite mathematical predictions and might eventually make testable ones. If these theories are correct, and if they predict multiverses, then we have indirect evidence for multiverses, even if we can't observe other universes directly. Second, some multiverse theories do make predictions, just subtle ones. For example, if the string landscape is correct, we should expect to find ourselves in a universe with physical constants that aren't especially special or fine-tuned, except insofar as they're required for observers to exist. The cosmological constant is a good example. It's incredibly small compared to what particle physics theories would naively predict, but it's not zero. The multiverse with anthropic selection predicts something like this: small enough for galaxies to form, but not so special that it requires a detailed explanation. Third, even if other universes are unobservable in principle, we might find evidence of interactions at the boundaries. If eternal inflation is correct, bubble universes occasionally collide as they form. Such a collision might leave an imprint in the cosmic microwave background, a circular pattern of slightly different temperatures. Several groups have looked for such signatures, and while nothing definitive has been found, the possibility remains open. Finally, defenders argue that even if we can't test multiverse theories directly, they may be necessary for a complete understanding of physics. If our best theories of quantum mechanics and cosmology inevitably lead to multiverses, and if those theories are correct, then the multiverses exist whether we like it or not. Science isn't just about making predictions, it's also about understanding reality. And if reality includes multiple universes, then understanding that is part of the scientific enterprise. The fine-tuning problem. One of the strongest motivations for taking multiverses seriously comes from what's called the fine-tuning problem. This is the observation that many physical constants and initial conditions of our universe seem to be delicately balanced, such that even small changes would make life impossible. Consider the strength of gravity. If gravity were much stronger, stars would burn out quickly, not giving planets time to cool and life time to evolve. If gravity were much weaker, matter wouldn't clump into galaxies and stars in the first place. The range that allows for something like our universe is narrow. Or consider the mass of the electron. If it were significantly different, atoms wouldn't form stable molecules. Chemistry, as we know it, would be impossible. Or the strength of the strong nuclear force, which holds atomic nuclei together, too weak, and atoms heavier than hydrogen wouldn't exist, too strong, and hydrogen would fuse into heavier elements in the early universe, leaving no hydrogen for stars and water. There are dozens of these examples. Some physicists estimate that the probability of getting a universe capable of supporting complex structures, like stars and planets, let alone life, is absurdly small if you randomly select values for all the constants. Now, this might seem like evidence for design. If the universe appears fine-tuned for life, maybe it was tuned by some intelligence. This is the argument from design, and it has a long history in philosophy and theology. But the multiverse offers a different explanation. If there are many universes with different physical constants, then we should expect to find ourselves in one of the rare ones that permits complex structures and life. Not because it was designed that way, but because those are the only universes where observers can exist to ask the question. This is an application of the anthropic principle. The fine-tuning isn't surprising because we're selecting from a biased sample. We can only observe universes that are capable of producing observers. It's like being surprised that you won the lottery, when you're only aware of lottery results because you won. If you hadn't won, you wouldn't be thinking about it. Critics of this anthropic reasoning point out that it doesn't really explain the fine-tuning. It just shifts the question. Instead of asking why our universe has these particular values, we're now asking why the multiverse produces universes with many different values. And we need a theory to tell us the distribution of values, which requires understanding the underlying physics. But defenders argue that it does explain something. In a universe with fixed physical constants, the fact that we can exist seems miraculous. In a multiverse, it's expected. The anthropic principle doesn't tell us everything, but it does change how we think about fine-tuning, making it less mysterious and more statistical. Quantum decoherence and the classical world. Let's return to the many worlds interpretation for a moment, because there's an important development we need to discuss: decoherence. This is the process by which quantum superpositions appear to collapse into definite states, not through any mysterious collapse mechanism, but through ordinary quantum interactions with the environment. Here's how it works. Imagine you have a quantum system in a superposition of two states. In isolation, this system could remain in superposition indefinitely, maintaining quantum coherence between the two states. But in practice, no system is perfectly isolated. It interacts with surrounding particles, photons, air molecules, thermal radiation, all the countless things that make up an environment. Each interaction entangles the system with its environment. Information about the system's state leaks out into the environment. And once enough information has leaked out, the different branches of the wave function become so different that quantum interference between them becomes impossible to detect. For all practical purposes, the superposition has collapsed, even though mathematically it still exists. This is decoherence. It doesn't solve the measurement problem by itself. It doesn't explain why we see one outcome rather than another, but it explains why the quantum world appears classical. It explains why we don't see macroscopic objects in superposition, why cats are alive or dead but not both, why measurement outcomes appear definite. In the context of many worlds, decoherence is the branching mechanism. When a quantum measurement happens, decoherence causes different outcomes to separate into different branches. The branches continue to exist in the universal wave function, but they can no longer interfere with each other. They've become, for all practical purposes, separate realities. This was a major development for many worlds, because early critics argued that the interpretation couldn't explain why we see definite outcomes. Decoherence provided the answer. The outcomes are definite within each branch, even though all outcomes exist across the full wave function. Decoherence has been studied extensively, both theoretically and experimentally. Physicists can calculate decoherence timescales for different systems. For microscopic systems like individual atoms, decoherence can be delayed using careful isolation techniques. For macroscopic systems, decoherence happens almost instantaneously, in less than a trillionth of a second. This explains why we never see quantum effects at human scales. It's not that quantum mechanics doesn't apply to big things. It does. But decoherence happens so fast for large objects that quantum superpositions vanish before we could ever detect them. The quantum world and the classical world aren't separate realms with different laws. They're the same reality, but decoherence makes large things behave classically, while small, isolated things can maintain quantum coherence. The problem of probability in many worlds. One of the deepest challenges for the many worlds interpretation is explaining probability. In Copenhagen quantum mechanics, outcomes are fundamentally random. When you measure a quantum system, you get one result or another with certain probabilities, and there's nothing determining which outcome you'll get. The randomness is built into nature at the deepest level. In many worlds, every outcome happens. When you measure an electron's spin, there's a version of you that sees spin up, and another version that sees spin down. Both versions are equally real. So why does it feel like outcomes are random? Why do we talk about probabilities at all? This is called the probability problem in many worlds, and it's been debated extensively. The question is, how do you derive the Born rule, the fundamental rule that tells you how to calculate quantum probabilities from a deterministic theory where all outcomes occur? Several approaches have been proposed. One, pioneered by David Deutsch and David Wallace, uses decision theory. They argue that if you're a rational agent making decisions in a branching universe, you should act as if you assign probabilities to different branches according to their quantum measure, not because you're actually more likely to end up in one branch than another. That doesn't even make sense because you end up in all of them, but because the quantum measure tells you something about the structure of the branches. Another approach, developed by Lev Weidman and others, focuses on the self-location uncertainty. Before a measurement, you don't know which branch you'll experience yourself to be in. The quantum measure determines the right way to quantify your uncertainty about your future self-location. These are subtle arguments, involving careful thinking about what probability means and how rational agents should reason in a branching universe. Not everyone finds them convincing. Critics argue that they're making assumptions that aren't justified, or that they're circular, using probability to derive probability. But supporters argue that some assumptions are necessary. You can't derive everything from nothing. The question is whether the assumptions are reasonable and whether the resulting framework makes sense. And many physicists who work seriously with many worlds believe the probability problem has been solved, at least in principle, even if the details remain debated. Cosmic inflation and the beginning of everything. Let's dive deeper into inflation, because this is where some of the most concrete evidence for multiverse ideas comes from. Inflation was proposed in 1981 by Alan Guth and independently by Andre Linde and others to solve several problems with the standard Big Bang model. The first problem was the horizon problem. When we look at the cosmic microwave background, we see that distant regions of the universe, regions that are on opposite sides of the sky and that have never been in causal contact, have almost exactly the same temperature. How did they coordinate to be so similar if light has never traveled between them? Inflation solves this by proposing that before the slower expansion we call the Big Bang, there was a period of much faster expansion. All the regions we can see today came from a tiny patch that was in causal contact before inflation began. That's why they're so similar. Inflation then stretched this patch to enormous size, far larger than our current observable universe. The second problem was the flatness problem. The universe appears to be spatially flat, meaning its geometry is Euclidean on large scales. But flatness is unstable in the standard Big Bang model. Any deviation from perfect flatness grows over time. To get a universe as flat as ours is today, the early universe would have needed to be flat to absurd precision, requiring fine-tuning to dozens of decimal places. Inflation solves this too. Exponential expansion stretches space so much that any curvature gets smoothed out. It's like inflating a wrinkled balloon. The more you inflate it, the smoother the surface becomes. After enough inflation, the universe becomes extremely flat, regardless of how it started. The third problem was the absence of magnetic monopoles. Some particle physics theories predict that the early universe should have produced enormous numbers of magnetic monopoles, exotic particles that are magnetic charges without opposite poles. But we've never detected any. Inflation explains this by diluting them. If monopoles formed before inflation, inflation would spread them so thin that we'd never find one. These solutions made inflation attractive, but what really convinced cosmologists was its predictions. Inflation predicts that quantum fluctuations in the inflaton field, the field driving inflation, should leave an imprint in the density of matter after inflation ends. These tiny density variations should show up in the cosmic microwave background as temperature fluctuations. And they do. Observations from satellites like COBE, WMAP, and Planck have measured these fluctuations with extraordinary precision. The pattern matches inflation's predictions remarkably well. The fluctuations are nearly scale invariant, meaning they have roughly the same amplitude at all sizes, just as inflation predicts. They're Gaussian, meaning their statistical distribution is a bell curve, just as quantum fluctuations should be. And they're adiabatic, meaning density and temperature fluctuations are correlated in the way inflation predicts. This is powerful evidence that something like inflation happened. It's not absolute proof. Inflation isn't the only theory that can explain these features, but it's the simplest and most successful explanation we have. Eternal inflation and the multiverse. Now here's where inflation leads to multiverses. The simplest inflation models have a field, the inflaton, sitting at a high energy value. This high energy drives exponential expansion. Eventually, quantum fluctuations push the field down to a lower energy state in some regions, and inflation ends in those regions. But in other regions, inflation continues. The key insight is that inflation expands space faster than these transitions happen. Even though regions are constantly exiting inflation, the inflating regions grow faster, creating more volume, more opportunities for new regions to exit in an endless cascade. This is eternal inflation. Once it starts, it never completely stops. It creates a fractal-like structure of bubble universes embedded in an eternally inflating background. Each bubble is a universe like ours, with its own Big Bang, its own history, its own galaxies and stars. Different models of inflation make different predictions about the details of this multiverse. In some models, the bubbles can collide, leaving observable signatures. In others, they're forever separated by the inflating space between them. In some, the physics is the same in every bubble. In others, connected to string theory, different bubbles crystallize with different physical constants. The eternal nature of inflation means it produces not just many universes, but infinitely many. Every possible way for inflation to end, every possible fluctuation pattern, every possible sequence of quantum events occurs somewhere in the eternally inflating multiverse. This is controversial, even among physicists who accept basic inflation. Some argue that eternal inflation relies on extrapolating the theory beyond where we have evidence. We have good reasons to think inflation happened in our universe, but assuming it works the same way everywhere, for all time, might be a step too far. Others argue that eternal inflation is hard to avoid once you accept inflation at all. The same quantum fluctuations that give us the cosmic microwave background structure also drive eternal inflation. You can't have one without the other, or at least, it's very difficult to construct models that give us the inflation we observe without also giving us eternal inflation. String theory and the landscape. String theory emerged in the 1970s and 80s as a potential theory of everything, unifying quantum mechanics and general relativity, explaining all particles and forces in a single mathematical framework. The core idea is simple. What if the fundamental constituents of reality aren't point particles, but tiny, vibrating strings? Different vibration modes of these strings correspond to different particles. A string vibrating one way is an electron, another way a photon, yet another a graviton, the hypothetical particle that carries the gravitational force. This would explain why there are so many different types of particles. They're all just different notes played by the same fundamental string. The mathematics of string theory is beautiful, but requires extra dimensions. In most versions, there are 9 dimensions of space and 1 of time, for a total of 10 dimensions. The 6 extra dimensions beyond the 3 we experience must be curled up into tiny, compact shapes. For a long time, string theorists hoped there would be a unique way to curl up these dimensions, leading to a unique set of predictions for particle physics. But as they explored the mathematics more deeply, they discovered the landscape. Approximately 10 to the power of 500 different ways to compactify the extra dimensions, each giving different physics in the 4 large dimensions. This was both disappointing and illuminating. Disappointing because it meant string theory doesn't uniquely predict the physics we observe. There's no single string theory that says, this is how the universe must be. Instead, there's a vast landscape of possibilities, but illuminating because, combined with eternal inflation, it offers an explanation for the apparent fine-tuning of physical constants. If eternal inflation produces infinitely many bubble universes, and if string theory's landscape gives different physics in different bubbles, then the multiverse explores the entire landscape. Every possible compactification occurs somewhere. Most universes in this landscape are sterile. The constants are wrong for atoms to form, or for stars to burn, or for structure to develop. But in a tiny fraction of bubbles, the constants happen to be right, and necessarily we find ourselves in one of those rare bubbles, because those are the only ones where observers can exist. This anthropic explanation for fine-tuning is controversial. Some physicists embrace it as a pragmatic solution to a genuine puzzle. Others see it as giving up on finding deeper explanations. If we can't calculate why the electron mass has its observed value, but just say it varies across the multiverse and we're in a universe where it has this value, have we really explained anything? The debate touches on deep questions about what science should do. Should it predict every observable quantity from first principles? Or is it enough to show that observed quantities lie within a range of possibilities, with anthropic selection explaining why we observe particular values? the measurement problem revisited. Let's return once more to the quantum measurement problem, because it's really the heart of why many physicists take many worlds seriously. The problem is this: quantum mechanics has two different rules for how systems evolve. Rule 1. When you're not measuring a system, it evolves according to the Schrödinger equation. This evolution is smooth, deterministic, and linear. Superpositions stay superpositions. Information is preserved. Everything is mathematically elegant. Rule 2. When you measure a system, the wave function collapses. Superpositions suddenly become definite states. The evolution is discontinuous, random, and non-linear. Information about the other possibilities is lost. The elegance breaks down. This is weird. Why should measurement be special? What counts as a measurement? Where exactly does the collapse happen? When you measure an electron, does the wave function collapse when the electron interacts with your detector? When the detector displays a result? When you look at the detector? When you become consciously aware of the result? The Copenhagen interpretation basically says, don't worry about it. Measurement is just fundamentally different from other physical processes. The collapse is real, it's random, and that's how nature works. Use Rule 1 for quantum systems, Rule 2 for measurements, and you'll get predictions that match experiments. What more do you want? But many physicists want more. They want a unified framework where the same rules apply to everything. They don't want to treat measurement as metaphysically special, and they certainly don't want consciousness to play a fundamental role in physics. The many worlds interpretation eliminates Rule 2 entirely. There's only Rule 1. The wave function always evolves according to the Schrödinger equation. Always. No exceptions. Measurement is just a particular type of quantum interaction, one that entangles the measured system with the measuring device and then with the environment. What looks like collapse is actually decoherence. The different outcomes don't disappear. They continue to exist in different branches of the wave function, unable to interfere with each other. From inside any branch, it looks like a definite outcome was randomly selected. But from the outside, looking at the full wave function, every outcome occurs. This is philosophically elegant. One rule instead of two. Determinism instead of fundamental randomness. No special role for measurement or consciousness. Everything emerges from the smooth evolution of the universal wave function. But it comes at a cost. Accepting that all those other branches are real. That every time a quantum event occurs, reality splits into multiple parallel versions. That there are countless copies of you experiencing different outcomes, all equally real, forever beyond your awareness. Many physicists think this cost is worth paying. Others think it's absurd. The debate has continued for over 60 years and shows no sign of resolution. Alternative interpretations. It's worth noting that many worlds isn't the only alternative to Copenhagen. There are other interpretations of quantum mechanics, each with its own strengths and weaknesses. Pilot wave theory, also called de Broglie-Bohm mechanics, proposes that particles always have definite positions, guided by a quantum wave that evolves according to the Schrödinger equation. The wave is real, and so are the particle positions. When you measure a particle, you're just revealing its position, which was always definite. The apparent randomness comes from our ignorance of the precise initial positions. This is deterministic and doesn't require splitting universes, but it's non-local, meaning influences can travel faster than light, though in a way that can't be used for signaling. And it treats position as fundamentally special, which seems arbitrary since quantum mechanics normally treats position and momentum symmetrically. Objective collapse theories propose that the wave function doesn't evolve smoothly all the time. Instead, it undergoes real, physical collapses, not just during measurements, but continuously, for all systems. These collapses are extremely rare for small systems, but become frequent for large systems, which is why large objects behave classically. This keeps a single universe and explains the classical world, but it requires modifying the Schrödinger equation. The modifications are chosen to be small enough that we haven't detected them yet, but potentially large enough to test in future experiments. So far, no evidence for such collapses has been found. Relational quantum mechanics proposes that quantum states are not absolute, but relative to observers. The wave function describes your information about a system, not the system itself. When you measure a system, you update your information, but other observers might have different information and thus different wave functions for the same system. This avoids collapse and many worlds, but at the cost of giving up on an objective description of reality. There's no fact of the matter about the state of a quantum system, only facts about relationships between systems and observers. Each interpretation has passionate defenders and critics. What's remarkable is that they all make the same experimental predictions. Quantum mechanics works. Everyone agrees on that. But what it means, what's really happening in the quantum world, remains deeply mysterious despite a century of study. Testing the multiverse. Given that other universes are by definition unobservable, how could we ever gather evidence for multiverse theories? This seems like a fundamental obstacle. But physicists have proposed several approaches. First, as mentioned earlier, colliding bubble universes might leave signatures in the cosmic microwave background. If our bubble collided with another bubble during inflation, the collision would create a circular pattern of temperature variations in a particular direction. Several research groups have searched for such patterns, analyzing Planck satellite data with sophisticated algorithms. So far, nothing definitive has been found, but the searches continue. Second, the string landscape makes statistical predictions. If we live in a randomly selected universe from the landscape, we can ask, what should we expect to observe? The cosmological constant is the best example. In the landscape, most universes have either much larger or much smaller cosmological constants than ours. The anthropic constraint is that it can't be too large, or galaxies wouldn't form. Given this constraint, our observed value is roughly what you'd expect from a random draw. Not too small, not at the maximum allowed value, but somewhere in between. This isn't proof, but it's suggestive. If we observed a cosmological constant that was absurdly small, say 1,000 times smaller than what anthropic arguments allow, that would be evidence against the landscape multiverse. The fact that it's not that small is consistent with the multiverse, though of course it's also consistent with other explanations. Third, many worlds makes predictions about quantum computing and quantum information. If branches are real, then quantum computers aren't just calculating with superpositions, they're actually performing computations across multiple branches of the multiverse. The branches interfere, allowing quantum computers to solve certain problems much faster than classical computers. The success of quantum computing is thus, in a sense, evidence for many worlds. Not conclusive evidence, other interpretations also explain quantum computing, but it's harder to understand quantum computation if you think the superposition collapses rather than evolving into multiple branches. Fourth, we might find evidence that our theories inevitably lead to multiverses. If string theory turns out to be correct and unavoidably produces the landscape, and if inflation is correct and unavoidably becomes eternal, then we have strong indirect evidence for multiverse, even without direct observation. This is analogous to evidence for black holes. We can't see inside a black hole's event horizon. By definition, nothing can escape to tell us what's there. But we have overwhelming evidence that black holes exist because general relativity predicts them. General relativity is extremely well tested, and we observe phenomena that match what black holes should produce. Similarly, if our best tested theories predict multiverses as an unavoidable consequence, then believing in those theories means believing in multiverses, whether we can see other universes or not. The anthropic principle in detail. The anthropic principle deserves deeper examination because it's central to many multiverse arguments. The term was coined by physicist Brandon Carter in 1973, though the idea is older. The weak anthropic principle simply states that our observations are subject to selection bias. We can only observe universes that are capable of producing observers. This seems obvious to the point of being trivial, but it has important implications. Imagine the constants of nature vary across a multiverse. In most universes, conditions are wrong for complex structures. But in a small fraction, conditions are right. Where do we find ourselves? Necessarily in one of the rare, suitable universes. Not because we're special or because the universe was designed for us, but because those are the only universes where anyone can exist to ask the question. This is like asking why we find ourselves on a planet with liquid water, breathable air, and moderate temperatures. Not because these conditions are common in the universe, they're extremely rare, but because those are the only planets where beings like us can evolve to wonder about such things. The strong anthropic principle goes further, suggesting that the universe must be such as to admit conscious observers at some point. This seems to imply purpose or design, and most physicists reject it as unscientific. But the weak version is more widely accepted, at least as a logical principle. The controversy comes when using it as an explanation. If you observe some property that seems finely tuned, and you explain it by saying, it varies across the multiverse, and we observe this value because it's compatible with our existence, have you explained anything? Or have you just given up on finding a deeper reason? Some physicists argue that anthropic explanations are legitimate when they're the best available. If a property genuinely varies across a multiverse with no deeper pattern, then anthropic selection is the only explanation possible. Asking, but why does it vary that way? Might be like asking, why do laws of logic exist? Some questions might not have answers beyond, that's how things are. Others argue that we should never accept anthropic explanations until we've exhausted all other possibilities. Maybe there is a deeper reason why constants have the values they do. Maybe future theories will calculate them from first principles. Giving up and invoking the anthropic principle might prevent us from finding these deeper explanations. The debate is ongoing, and it touches on fundamental questions about what constitutes a scientific explanation and when we should accept that some facts might be contingent rather than necessary. Philosophical implications. The multiverse, if real, has profound philosophical implications. It challenges our intuitions about existence, identity, probability, and the nature of reality itself. Consider personal identity. In a quantum multiverse, there are countless versions of you, experiencing different outcomes of quantum events. Are all of them you? If you're about to make a quantum measurement, should you care equally about all the future versions that will result? Or should you care more about versions that have higher quantum measure? This isn't just abstract philosophy. It affects how you should make decisions if many worlds is correct. Suppose you're offered a quantum gamble, a quantum coin flip. Heads, you win $1 million. Tails, you win nothing. Should you take the bet? In Copenhagen quantum mechanics, it's a straightforward probability problem. You have a 50% chance of winning, 50% of losing. You calculate expected value and decide accordingly. In many worlds, both outcomes happen. There's a version of you that wins and a version that loses. The question is, from your current perspective, how should you value these future selves? Decision theory, in many worlds, requires careful thinking about these issues. The multiverse also affects questions about the meaning of life. If every possible history occurs somewhere in the multiverse, does anything really matter? Some people find this thought disturbing, suggesting that nothing is truly significant if everything happens. But others find it liberating, or even comforting. Your choices still matter to you and those around you in your branch of reality. The fact that other versions make different choices doesn't diminish the importance of what you do. Each branch is a full, rich reality with genuine consequences for the beings within it. There are also questions about probability and explanation. In a multiverse where everything possible happens, can we explain anything? Or does explanation become impossible because every outcome occurs? This gets technical, but the basic issue is, if you want to explain why you observe X rather than Y, you can't just say both X and Y occur in the multiverse. You need to explain why X is more probable in your branch, or why you find yourself in an X branch rather than a Y branch. The anthropic principle provides some explanatory power, but only for properties related to the existence of observers. The ultimate question, why anything? Even if we accept that multiverses exist, they don't answer the deepest question. Why is there something rather than nothing? Why does anything exist at all? Tegmark's Level 4 multiverse might seem to address this. If all mathematical structures exist, then existence is in some sense inevitable. Mathematics doesn't depend on anything physical. Mathematical truths are eternal and necessary. If reality is mathematics, then reality is necessary too. But this just pushes the question back. Why do mathematical structures exist? Why is mathematics possible? Why does logic work the way it does? Some philosophers argue these questions are meaningless. Asking, why does logic exist, is like asking, what's north of the North Pole? The question assumes something that doesn't make sense. Logic and mathematics are preconditions for asking why questions. You can't ask why they exist without already assuming they exist. Others argue that these are genuine mysteries, perhaps ultimately unsolvable, but still worth contemplating. The existence of something rather than nothing might be the most fundamental fact about reality, and it might have no explanation. In the context of multiverses, the question becomes, why does the multiverse exist? If our universe is one bubble in an eternally inflating multiverse, what started inflation? If it's one branch of a quantum wave function, what determined the initial wave function? If it's one point in the string landscape, why does the landscape exist? These questions might have answers within physics. Maybe the multiverse is eternal, with no beginning, no cause, just an endless process of generation and branching. Maybe time itself emerges from something more fundamental, making questions about before or what caused meaningless. Or maybe these questions point beyond physics, into metaphysics, or theology, or simply into the unknown. Maybe existence is ultimately brute fact, requiring no explanation, admitting no explanation, objections and controversies. The multiverse idea faces numerous objections from physicists and philosophers. Let's examine the main criticisms. First, the untestability objection. If other universes are forever beyond observation, how is this different from believing in invisible fairies? Science requires empirical verification. Theories that can't be tested aren't science. Defenders respond that the multiverse isn't itself a theory. It's a prediction of other theories, like inflation and quantum mechanics, that are testable. We don't need to directly observe other universes if we have good reasons to believe the theories that predict them. Second, the Occam's razor objection. Science should prefer simpler explanations. Postulating infinitely many universes seems like the opposite of simplicity. Defenders respond that simplicity isn't about counting entities, but about the elegance of the fundamental theory. Many worlds, for example, has simpler fundamental laws than Copenhagen, even though it predicts more universes. One rule instead of two rules is simpler, even if that one rule implies many worlds. Third, the probability objection. If all outcomes occur in the multiverse, how can we say some are more probable than others? Doesn't the concept of probability become meaningless? Defenders point to quantum measure in many worlds and anthropic reasoning in the cosmological multiverse. These provide frameworks for understanding probability, even in a multiverse. It's subtle, but it works. Fourth, the fine-tuning objection, but from the other direction. Some argue that the multiverse doesn't solve fine-tuning, but makes it worse. Now we need to explain why the multiverse-generating mechanism exists and has the right properties to generate universes with varying constants. Isn't that an even bigger fine-tuning? Defenders argue that the multiverse-generating mechanisms, like eternal inflation, emerge naturally from relatively simple theories. We're not adding new fine-tuning. We're explaining apparent fine-tuning in our universe by showing it's not universal but statistical. Fifth, the meaning objection. If everything happens, doesn't that make life meaningless? If there's no uniqueness, no specialness to our universe, why should anything matter? This is more philosophical than scientific. Defenders argue that meaning comes from local context, from your experiences and relationships and choices, not from whether your universe is unique. Even in a multiverse, your life has meaning to you and those around you. The role of observation and consciousness. One of the strangest aspects of quantum mechanics is the role of observation. In the Copenhagen interpretation, observation causes wave function collapse. But what counts as observation? Does it require consciousness? Can a detector count as an observer if no conscious being looks at it? These questions have led some physicists and philosophers to propose that consciousness plays a fundamental role in quantum mechanics. The idea is that conscious observation is what collapses the wave function, converting quantum possibilities into classical actualities. This is highly controversial. Most physicists think consciousness is irrelevant to quantum mechanics. Observation just means interaction with a macroscopic system that causes decoherence. A detector records a measurement result whether or not anyone looks at it. The universe existed long before conscious beings evolved, and quantum mechanics work just fine. But some philosophers and physicists disagree. They argue that consciousness might be intimately connected with quantum collapse, or with the selection of which branch we experience in many worlds. The hard problem of consciousness, why we have subjective experiences at all, might be related to the measurement problem in quantum mechanics. These ideas are speculative and not widely accepted, but they're worth mentioning because they show how deep these questions go. The multiverse, quantum mechanics, and consciousness might all be connected in ways we don't yet understand. In many worlds, consciousness doesn't cause splitting, but it experiences splitting. Each version of you perceives one outcome, unaware of the other versions. Why do you experience this particular branch? That's the subjective uncertainty we discussed earlier. Before a measurement, you don't know which branch you'll find yourself experiencing. This raises questions about what makes you, you, across branches. Are all the branches equally you? If they're all experiencing different things, having different thoughts, making different decisions, in what sense are they the same person? These are hard questions without clear answers. Personal identity is puzzling even without multiverse theory. Adding multiple yous across different branches or different universes makes it even more confusing. Multiverse. In popular culture, the multiverse has captured public imagination partly because it appears frequently in science fiction and popular media. Movies, TV shows, books, and comics have explored parallel universes for decades. Sometimes these fictional multiverses resemble the physics proposals. Stories about quantum branching, where every choice creates a new timeline, echo many worlds. Stories about bubble universes with different physical laws resemble eternal inflation. Stories about simulated realities connect to the simulation hypothesis. But often, fictional multiverses work differently from the physics versions. They might have portals between universes, or ways to travel from one reality to another, or merged realities. Things that don't work in the actual physics proposals. This is fine. Fiction explores ideas for drama and entertainment, not scientific accuracy. But it can create confusion about what physicists actually propose. The many worlds interpretation doesn't let you visit other branches. Bubble universes are forever causally disconnected. The multiverse isn't about alternate history or parallel dimensions you can travel to. It's about the structure of reality, as described by our best physical theories. Still, the cultural impact is significant. The multiverse has become part of how people think about possibility and reality. It's influenced philosophy, theology, and even ethics. If multiple versions of you exist making different choices, does that change your moral responsibility? If other universes exist with vastly different conditions, does that change how you think about our universe? These cultural explorations, even when not scientifically accurate, serve a purpose. They help people grapple with the implications of these ideas, work through the philosophical puzzles, and think about what it means for our place in reality. The future of multiverse physics. Where is multiverse research headed? What developments might we expect in the coming years and decades? First, better observations of the cosmic microwave background and large-scale structure might provide evidence for or against eternal inflation. If we find signatures of bubble collisions, that would be strong evidence for the multiverse. If we can rule out such signatures with high confidence, it would constrain multiverse models. Second, developments in string theory might clarify whether the landscape is real and how many possibilities it contains. If string theorists find a unique solution after all, that would undermine the landscape multiverse. If they confirm that the landscape is unavoidable, that would strengthen multiverse arguments. Third, experiments testing quantum mechanics at larger scales might help discriminate between interpretations. If we can maintain quantum superposition for increasingly large objects, that might favor many worlds over collapse theories. If we find evidence for spontaneous collapse, that would support objective collapse theories over many worlds. Fourth, advances in quantum computing might shed light on the interpretation of quantum mechanics. If quantum computers can perform calculations that seem to require resources beyond what exists in our observable universe, that might be evidence for many worlds, where the computation is distributed across branches. Fifth, cosmological observations might discover unexpected features that constrain multiverse theories. For example, if we found that certain constants vary across our observable universe, that would dramatically change the discussion. Or, if we found evidence that the universe is closed rather than flat, that would affect inflation models. Sixth, theoretical developments might propose new tests or new implications of multiverse theories. Physics is full of surprises. Ideas that seem untestable sometimes become testable with clever new approaches. The multiverse will likely remain controversial for some time. But the debate is productive, forcing physicists to clarify their ideas about what science can and should explain, how to deal with apparently untestable predictions, and what role anthropic reasoning should play in physics, what we can know and what we cannot. There's a fundamental epistemological question about multiverses. Are there limits to what we can know? If other universes are truly unobservable, then yes, there are things we can never know. We can't know what conditions are like in a bubble universe, a trillion light-years away in the eternally inflating multiverse. We can't know what it's like to experience the other branches of the quantum wave function. We can't know what universes with different mathematical structures would be like. This bothers some people. Science is supposed to be about knowledge through observation. If something is unobservable in principle, can we ever really know it exists? But defenders point out that we already accept many things we can't directly observe. We believe in quarks, even though we can't see individual quarks. We believe in black hole interiors, even though nothing can escape to tell us what's inside. We believe in the far side of the observable universe, even though light from there hasn't reached us yet. Science isn't just about direct observation, it's about inference, about building theories that explain what we do observe, and following those theories to their logical conclusions. If our best theories predict multiverses, then believing in multiverses is rational, even if we can't observe them directly. There's also a question about what kind of knowledge we should seek. Even if we can't know everything about other universes, understanding that they exist and how they relate to ours is valuable knowledge. It changes how we think about our universe, about fine-tuning, about the nature of reality. Some philosophers argue for a distinction between what we can know in principle and what we can know in practice. Other universes might be unobservable in practice, but not in principle. Perhaps vastly advanced civilizations could find ways to detect them that we can't imagine. Or perhaps future theories will reveal unexpected connections. But some aspects of the multiverse might be unknowable in principle. If quantum branches are truly separate after decoherence, with no possible interference, then they're unknowable to each other fundamentally, not just practically. If bubble universes are beyond our cosmic horizon and space is expanding too fast for light to ever cross the gap, then they're fundamentally unobservable. These limits might be frustrating, but they're also profound. They tell us something deep about the structure of reality, about what's possible and what isn't. Understanding the limits of knowledge is itself a kind of knowledge, the meaning of it all. So what does it mean if the multiverse is real? How should it change how we think about ourselves and our place in existence? First, it's humbling. If the multiverse exists, our universe is an infinitesimally small part of reality. Not just our planet or our galaxy or our observable universe, but our entire universe, with all its galaxies and history and vastness, is just one bubble, one branch, one possibility among infinite others. This is a continuation of a trend that's been ongoing for centuries. Copernicus showed that Earth isn't the center of the solar system. Later discoveries showed that our solar system isn't the center of the galaxy. Our galaxy isn't the center of the universe, and there might not be a center at all. The multiverse is the next step. Our entire universe isn't the totality of existence. But second, it's also empowering. The fact that we can even conceive of the multiverse, that our minds evolved in this tiny corner of reality, can nevertheless grasp the possibility of infinite other realities, is remarkable. We might be small, but we're not insignificant. We're the universe understanding itself, or at least one small part of the multiverse, understanding the whole. Third, it suggests that existence is far richer and stranger than we imagined. The multiverse isn't just more of the same. It's fundamentally different possibilities. Universes with different laws, different structures, different ways of being. Reality is not just vast in quantity, but diverse in quality. Fourth, it raises questions about uniqueness and significance. If everything that can happen does happen somewhere, does anything have special meaning? Or does meaning come from context, from relationships, from the fact that even if infinite versions exist, each one is experiencing a unique perspective? These aren't questions with definitive answers. They're points for contemplation, areas where science touches philosophy and personal meaning. The history of infinite possibilities. The idea of multiple worlds isn't new. Ancient Greek philosophers speculated about infinite worlds. Atomists like Democritus and Epicurus imagined that atoms falling through the void would occasionally collide and form worlds, with infinitely many such worlds existing simultaneously throughout infinite space. Medieval philosophers debated whether God could have created multiple worlds. Most concluded that he could have, but chose to create only one. But the possibility was acknowledged, at least as a thought experiment. In the 17th century, Giordano Bruno proposed that the universe contained infinitely many worlds, each with its own planets and life. This was one of the reasons he was burned at stake by the Inquisition in 1600, though his cosmological views were entangled with theological heresies that made him dangerous to the Church. In the 18th and 19th centuries, various philosophers and scientists speculated about parallel worlds or alternate realities. Kant discussed the possibility of multiple worlds existing in different parts of space. Later thinkers explored the idea of alternate histories, worlds where events unfolded differently. But these were all philosophical speculations, not scientific theories. The modern multiverse is different because it emerges from mathematics and physics, from theories that make testable predictions about our universe, and that, as consequences of their internal logic, also predict other universes. This is why many physicists take it seriously, even though they can't observe other universes. It's not that anyone wanted to believe in multiverses. It's that the theories we've developed to explain what we do observe seem to require them. Competing theories and future resolution. Not all physicists accept multiverse theories, and there are alternative frameworks that avoid multiverses while still addressing the same problems. Some physicists work on finding unique solutions in string theory, ways to select one point in the landscape rather than accepting the whole landscape as real. Various approaches have been proposed, using symmetry principles, finding constraints from consistency requirements, or developing new mathematical techniques to narrow down possibilities. Others work on alternatives to inflation that explain the observed features of the cosmic microwave background without eternal inflation. These theories are less developed than inflation, but remain active areas of research. Some physicists develop modified versions of quantum mechanics that avoid both many worlds and the problematic aspects of Copenhagen. Objective collapse theories, pilot wave theories, and other approaches continue to be refined and tested. The resolution might come from unexpected directions. Perhaps future experiments will decisively favor one interpretation of quantum mechanics. Perhaps observations will find signatures of other universes or rule them out. Perhaps new theoretical developments will change the entire discussion. Or perhaps the multiverse question will remain unresolved for a long time, with different physicists adopting different frameworks based on their philosophical preferences and aesthetic judgments about what makes a good theory. Science doesn't always converge quickly on consensus. Sometimes debates continue for decades or longer, especially on foundational questions where empirical evidence is hard to obtain. The multiverse debate might be one of those long-running discussions, productive and important, even without definitive resolution. Practical implications. You might wonder, does any of this matter for everyday life? If the multiverse exists but we can't interact with other universes, why should anyone care besides theoretical physicists? There are a few answers. First, understanding reality is valuable in itself. Humans are curious creatures. We want to know how things work, what's real, what our place is in the cosmos. The multiverse, if real, is a fundamental fact about existence, worth understanding for its own sake. Second, these ideas influence how we think about other questions. The fine-tuning problem affects discussions about the origin of the universe, about whether the universe was designed, about the relationship between physics and theology. The multiverse offers a naturalistic explanation for apparent fine-tuning, changing those discussions. Third, quantum mechanics and cosmology have practical applications. Quantum mechanics underlies all of chemistry, materials, science, and computing. Cosmology helps us understand the history and fate of the universe. Working on the foundations of these theories, even on seemingly abstract questions like interpretation, can lead to practical insights and applications. Fourth, thinking about multiverses stretches our imagination and challenges our assumptions. It's a form of intellectual exploration that develops skills applicable to other areas: logical thinking, careful reasoning, comfort with abstraction, and willingness to follow arguments wherever they lead. Finally, there's cultural impact. The multiverse has entered popular consciousness. It affects how people think about possibility, reality, and meaning. Understanding what physicists actually propose versus what appears in fiction helps people engage more thoughtfully with these ideas. The limits of science. The multiverse debate also raises questions about the limits of science. Are there questions science can't answer? Are there aspects of reality forever beyond scientific investigation? Traditional philosophy of science, following Karl Popper, emphasized falsifiability. A theory is scientific if it makes predictions that could be proven wrong. If a theory can't be falsified, it's not science, but metaphysics. By this standard, multiverse theories seem problematic. If other universes are unobservable, how can you falsify the claim that they exist? You can't. Any observation is compatible with the multiverse. But modern philosophy of science has become more nuanced. Falsifiability is important, but not the only criterion. Theories should also be explanatory, coherent with other well-established theories, and ideally make some predictions, even if not all aspects are testable. By these broader standards, multiverse theories might qualify as scientific. They explain fine-tuning. They emerge from well-tested theories like quantum mechanics and inflation, and they make some predictions, like the statistical distribution of constants we should expect to observe. Still, there's something unsatisfying about a theory whose central claim can't be directly tested. Some physicists argue this indicates we need new approaches, new ways of thinking about how to do physics, when the objects of study are fundamentally unobservable. Others argue that this just reflects the nature of reality. We've reached domains where observation becomes impossible, but that doesn't mean we should stop theorizing. Math and logic can still guide us, and we can follow theories to their conclusions, even when those conclusions outstrip our ability to observe. This might represent a shift in how science works, from direct observation and experiment to more indirect inference and theoretical reasoning. Some see this as a natural evolution. Others see it as a dangerous departure from what makes science successful. The debate continues, and it's not clear how it will resolve. But it's an important conversation about the nature and limits of scientific knowledge, the psychological appeal of multiverses. Why do multiverse ideas resonate so strongly with many people? There's something compelling about the notion of parallel worlds, alternate versions of ourselves, infinite possibilities. Part of it is wish fulfillment. The many worlds interpretation suggests that every possible choice you could make, you do make in some branch. Regret a decision? In another branch, you chose differently. Wonder what your life would be like if you'd taken another path? In another branch, you took it. This doesn't diminish the importance of your choices in this branch. The other yous are separate, inaccessible, forever beyond your awareness. But there's still something comforting or fascinating about the idea that all possibilities are explored. Part of it is the appeal of vastness. Humans are drawn to the big picture, to understanding the totality of existence. The multiverse represents the ultimate big picture, reality in its fullest extent. It satisfies our desire to know what's really out there beyond what we can see. Part of it might be existential. If our universe is just one among many, that might make the apparent absurdity or cruelty of existence easier to bear. We're not in a unique creation where suffering and death are parts of the only reality. We're in one of countless realities, and presumably in some others, things are better. Or conversely, some people find the multiverse disturbing or nihilistic. If everything happens, nothing is special. If there are infinite yous, you're not unique. If all outcomes occur, your choices don't matter in any cosmic sense. These psychological reactions aren't arguments for or against the multiverse's existence. Reality doesn't care about our comfort or discomfort. But they're interesting because they show how deeply these ideas affect us, how they touch on fundamental questions about meaning and identity. Theological implications. The multiverse has implications for theology and religious thought, though what those implications are depends on one's religious framework. Some religious thinkers embrace the multiverse. If God is omnipotent and creates all possible worlds, that's consistent with multiverse theory. The level 4 multiverse, where all mathematical structures exist, could be seen as an expression of divine creativity. God doesn't just create one universe, but all possible universes. Others see the multiverse as threatening to faith. If the appearance of design in our universe can be explained by anthropic selection across a multiverse that removes one argument for God's existence, we don't need a fine-tuner if fine-tuning is explained statistically. But defenders of design arguments note that the multiverse just pushes the question back. Why does the multiverse generating mechanism exist? Why does it have the properties it does? Even if our universe's constants are explained anthropically, the underlying laws that generate the multiverse might themselves show evidence of design. There are also questions about divine action. If God created a multiverse, does he interact with all branches or all bubbles? Are there infinite incarnations, infinite redemptions, infinite divine plans? These questions don't have clear answers and touch on deep mysteries in theology. Some theologians argue that the multiverse is irrelevant to faith. Religion is about meaning, morality, and relationship with the divine, not about the physical structure of reality. Whether there's one universe or infinitely many doesn't change the fundamental questions of how to live, what's right and wrong, or what ultimate reality is. Others argue that cosmology does matter to theology. How we understand creation affects how we understand the Creator. If the multiverse exists, that tells us something about the nature of existence and possibly about the nature of whatever underlies existence. These discussions are ongoing, with thoughtful people on all sides. The multiverse challenges traditional theological frameworks, but also opens new possibilities for thinking about creation and divine action. Mathematical universes and Platonic realism. Tegmark's Level 4 multiverse relies on a philosophical position called mathematical Platonism or Platonic realism. This is the view that mathematical objects exist independently of human minds, in some abstract realm. Most mathematicians are Platonists in practice, even if they're not philosophically committed to it. When mathematicians discover a theorem, it feels like they're uncovering something that was already true, not inventing something new. The Pythagorean theorem was true before anyone proved it. Mathematical facts seem eternal and necessary. But where do mathematical objects exist? If numbers and geometrical shapes and functions aren't physical, where are they? The traditional Platonic answer is that they exist in a realm of forms, a non-physical reality more fundamental than the physical world. Tegmark's multiverse takes this seriously. If mathematical structures are real, and if reality is fundamentally mathematical, then all mathematical structures are real as physical universes. There's no separate Platonic realm. The mathematical structures are the universes. This is deeply weird, but also elegant. It explains why mathematics is so effective at describing physics. It's not that math is a language we use to describe reality. Math is reality. Physics is applied mathematics. Critics argue that not all mathematical structures could exist as physical universes. Some structures might be too simple, lacking the complexity needed for time, space, and causation. Others might be inconsistent in ways that prevent physical instantiation. Defenders respond that we shouldn't anthropomorphize what counts as a universe. A mathematical structure doesn't need time and space as we understand them to be a universe. It just needs to be a complete, consistent structure. Beings within that structure, if any exist, would experience it as their reality. This is highly speculative philosophy, and most physicists don't commit to level 4, but it represents the logical endpoint of taking multiverse ideas seriously. If we accept level 1, 2, and 3, why stop there? Why not accept all possible mathematical structures as existing? The role of symmetry and beauty. Throughout physics, symmetry and mathematical beauty have guided theory development. Einstein's relativity grew from the principle that the laws of physics should look the same in all reference frames. Quantum mechanics and the Standard Model are built on deep symmetry principles. Many physicists believe that the ultimate theory of everything will be beautiful, elegant, and symmetric. The universe's complexity should emerge from simple, fundamental rules. This aesthetic sense has been remarkably successful in guiding theoretical development. The multiverse challenges this expectation in some ways. If our universe is just one of countless possibilities, selected anthropically, then there's no reason to expect our particular universe to be especially elegant. Our physical constants might be random within the range that permits life, not determined by deeper principles. This troubles physicists who believe beauty should guide physics. They see the anthropic principle as a cop-out, a way of avoiding the search for deeper explanations by saying it's just random within the multiverse. But others argue that the multiverse itself might be beautiful and elegant at a deeper level. The fundamental theory that generates the multiverse, whether it's eternal inflation or many worlds quantum mechanics or string theory, might be elegant even if individual universes within it aren't. This shifts where we look for beauty. Instead of expecting our particular universe to manifest the ultimate elegance, we should look for elegance in the overall structure of reality, the multiverse as a whole. Whether this is satisfying depends on aesthetic preferences. Some physicists can accept it, others still hope for a unique, beautiful solution that predicts our exact universe without requiring anthropic selection. The information paradox. There's an interesting connection between multiverse ideas and black hole information paradoxes. Black holes seem to destroy information, which violates quantum mechanics. When matter falls into a black hole, information about its quantum state appears lost forever. Stephen Hawking showed that black holes emit radiation and eventually evaporate, but the Hawking radiation seems to be thermal, containing no information about what fell in. If the black hole completely evaporates, the information is gone, violating unitarity, the principle that information is conserved in quantum mechanics. Various solutions have been proposed. Maybe information is encoded in the Hawking radiation in subtle correlations. Maybe it's stored at the event horizon. Maybe black hole interiors connect to other universes, baby universes spawned by the collapse, carrying the information away into separate regions of the multiverse. This last possibility connects to some cosmological multiverse ideas. If black hole interiors spawn new bubble universes, then the multiverse might be self-reproducing, with black holes acting as seeds for new cosmic domains. Lee Smolin proposed cosmological natural selection. Universes that produce many black holes spawn many daughter universes, and the parameters that produce lots of black holes might also produce lots of stars and possibly life. The multiverse evolves over time with reproduction and selection. This is highly speculative, and most physicists don't take it as literally true, but it shows how multiverse ideas connect to other deep problems in physics, suggesting that understanding one might require understanding the others. Quantum immortality. One of the stranger implications of many worlds is something called quantum immortality. The argument goes like this: in many worlds, every possible outcome occurs. So if you're facing a life-threatening quantum event, there's always a branch where you survive. From the perspective of versions of you that die, the story ends. But from the perspective of surviving versions, you keep experiencing consciousness. As long as there's any quantum probability of survival, there's a branch where you survive. Following this logic to its extreme, you might be subjectively immortal. Every possible future where you remain conscious is experienced by some version of you. The versions that die can't experience death. So from your subjective perspective, you always find yourself in branches where you're alive. This is weird and disturbing. It suggests you might experience increasingly improbable survival in dangerous situations, always finding yourself in the lucky branch. It also raises questions about aging and natural death. If there's any quantum probability of your cells not deteriorating, there might be branches where you age very slowly or not at all. Most physicists dismiss quantum immortality as a misunderstanding of many worlds. The measure, the quantum probability weight, of branches where you survive a dangerous situation decreases. Most of your measure goes to branches where you die. The versions of you that survive are real, but increasingly improbable. Still, it's a thought-provoking implication that shows how strange many worlds becomes when you think about it seriously. It's one thing to say all outcomes occur. It's another to really contemplate what that means for subjective experience and identity. The computer simulation hypothesis revisited. Let's return briefly to the simulation hypothesis, because it connects to multiverse ideas in interesting ways. If our universe is a simulation, there might be many other simulations running on the same or different hardware. Each simulation would be a universe. But more intriguingly, simulations could nest. The simulators might themselves be in a simulation, and those simulators might be in a simulation. This creates a hierarchy of nested realities, each one simulated by the level above. How many levels might there be? If simulations are possible, and advanced civilizations run them, there could be many, many levels. Most conscious beings would be in simulations rather than base reality, whatever that is. This creates a strange multiverse where the structure is hierarchical rather than parallel. You're not in one of many equal universes. You're at some level in a tower of simulations. The simulation hypothesis also raises questions about physics. If we're in a simulation, the laws of physics are programming decisions. The programmers could change them. They could reveal themselves. They could intervene in ways that violate natural law. Some people find this possibility comforting, suggesting the existence of beings more powerful than natural law who might be interested in us. Others find it disturbing, suggesting we're not real in the way we think, just patterns in some computer. Philosophers debate whether there's a meaningful distinction between being really real and being a simulation. If a simulation is detailed enough that conscious beings arise within it, are those beings less real than unsimulated ones? Does it matter if you're made of atoms or of bits? These questions don't have clear answers, but they show how the multiverse concept, broadly understood, connects to foundational questions about the nature of reality and existence. Closing thoughts. Living with uncertainty. As we near the end of this exploration, it's worth reflecting on what we've learned and what remains unknown. The multiverse is not a confirmed fact. It's a possibility that emerges from our best theories, taken seriously by many physicists, but rejected or doubted by many others. We've seen that there are different types of multiverses: the infinite universe with distant regions, the bubble universes from eternal inflation, the quantum branches from many worlds, and the mathematical universes from Tegmark's hypothesis. Each has different evidence and different philosophical implications. We've explored the arguments for and against, the fine-tuning problem, the measurement problem in quantum mechanics, the testability objection, the role of beauty and simplicity in physics. We've seen that smart, thoughtful people disagree about these ideas. What should we conclude? Perhaps the most honest answer is uncertainty. The multiverse might be real. It might not be. We might find evidence that settles the question. We might not. This uncertainty is uncomfortable but also appropriate. Science is about following evidence and logic wherever they lead, but also about acknowledging when we don't know. Pretending to certainty when evidence is ambiguous isn't scientific. It's dogmatic. The multiverse debate exemplifies science at its best, grappling with deep questions, developing theories, testing predictions, arguing about interpretations, and slowly, painstakingly building understanding. The process is messy and uncertain, but that's how progress happens. For those of us watching from outside the research frontier, the multiverse offers something else, a sense of wonder. Whether it's real or not, the fact that we can conceive of it, that our theories point toward it, that reality might be so much vaster than we ever imagined, is extraordinary. We're apes on a small planet, looking out at the cosmos and trying to understand what's real. The fact that we can even formulate the question, are there other universes, is remarkable. The fact that we might someday answer it, one way or another, is even more remarkable. A universe of possibilities. Imagine standing at the shore again, looking out at that vast ocean. But now imagine that ocean is just a drop of water, and that drop is part of an infinite sea. And that sea exists in countless parallel versions, each slightly different. And all of these seas are just one possibility among infinite mathematical structures. This is what the multiverse suggests. Reality isn't just big, it's unimaginably, incomprehensibly vast. Not just in space or time, but in possibility itself. Every way things could be, might be, somewhere, somehow. If this is true, it changes how we think about existence. Our universe, for all its grandeur, is just one note in an infinite symphony, one page in an endless book, one possibility among infinite possibilities. But here's the profound part. We're conscious beings within this structure. We can understand, at least partially, the mathematics that describes it. We can formulate theories about the multiverse, even if we can't observe most of it. We can ask these questions and work toward answers. That makes us, in a sense, the universe reflecting on itself, or more accurately, one tiny part of an infinite multiverse reflecting on the whole. We're threads in an infinite tapestry, but threads that can see beyond themselves to glimpse the pattern. The journey continues. This exploration of multiverse theory has taken us through quantum mechanics, cosmology, string theory, philosophy, and the limits of science. We've encountered ideas that challenge our intuitions about reality, identity, probability, and existence itself. Some of these ideas might be correct, others might be wrong. Future observations and theoretical developments will clarify the picture. But even if the multiverse turns out not to be real, the journey has been worthwhile. Wrestling with these ideas has deepened our understanding of quantum mechanics, cosmology, and the scientific process itself. And if the multiverse is real, then we've discovered something profound about the nature of existence. We've learned that reality is far larger and stranger than we imagined. We've glimpsed the true scope of what exists. Either way, the questions we've explored are among the deepest humanity has ever asked. What is real? How big is reality? Are we alone? What is our place in existence? These aren't just scientific questions. They're philosophical and even spiritual questions. They touch on meaning, purpose, and our relationship to the cosmos. Science can inform our thinking about them, but it can't answer them completely. We each have to grapple with these questions in our own way. The wonder of not knowing. There's something beautiful about standing at the edge of knowledge, looking out into the unknown. We don't know if the multiverse is real. We might never know for certain, but we can wonder. We can theorize. We can explore the possibilities. This sense of wonder is precious. It's what drives science forward, what makes us human, what connects us to the cosmos. As long as there are mysteries to ponder and questions to ask, we have something to reach for. The multiverse represents the ultimate mystery, not just what exists beyond our cosmic horizon, beyond our quantum branch, beyond our universe, but whether reality is far vaster than we ever dreamed, whether existence itself is infinite in scope and possibility. We may be small, living our brief lives on a tiny planet, orbiting an ordinary star in a universe that might be just one among infinitely many. But we can look up. We can wonder. We can ask questions about the nature of everything. And in that wondering, that questioning, we transcend our smallness. We connect with something larger than ourselves. A final reflection. As you drift toward sleep tonight, consider this. Somewhere in the vast sweep of possibility, whether in distant regions of our infinite universe, in other bubbles of the eternally inflating multiverse, in other branches of the quantum wave function, or in other mathematical structures entirely, there might be other versions of you, other consciousnesses contemplating these same questions. You'll never meet them, never communicate with them, never even know they exist. They're forever beyond your reach, separated by distance, by decoherence, by the structure of reality itself. But in a sense, you're all part of the same grand pattern, the same exploration of possibility, the same expression of existence. Each version experiencing one perspective, one path through the infinite landscape of what could be. And here, now, in this particular branch, this particular bubble, this particular universe, you exist, conscious, aware, wondering about it all. That's not diminished by the possibility of other yous in other universes. If anything, it makes your existence more remarkable, more precious, because even in an infinite multiverse, this particular combination of experiences, memories, and moments is yours. This particular path through reality, with all its joys and sorrows, triumphs and struggles, is uniquely yours. No other version is experiencing exactly this. No other path is quite the same. So whether the multiverse is real or not, whether reality is one universe or infinitely many, your existence matters. Your choices matter. Your experiences are real and valid and significant. The multiverse, if it exists, doesn't diminish you. It contextualizes you, showing you as part of something vast and wonderful, but it doesn't erase you or make you less real. You're still here, still conscious, still part of this grand cosmic story. Farewell for now. We've journeyed far tonight, from the Copenhagen interpretation of quantum mechanics to eternal inflation, from the string landscape to level 4 mathematical structures, from black hole information to quantum immortality. We've explored arguments, examined evidence, and grappled with implications. The multiverse remains mysterious as consciousness, time, or existence itself. We've made progress understanding these things, but deep questions remain. That's as it should be. Reality doesn't owe us easy answers, but we can keep exploring, keep wondering, keep pushing at the boundaries of knowledge. That's what makes us human. That's what makes us part of the universe's effort to understand itself. So as you close your eyes and let sleep approach, let your mind wander through these infinite possibilities. Imagine other branches, other bubbles, other versions of reality, playing out their own stories. Imagine the vast multiverse, if it exists, in all its glory and strangeness, and know that whatever the truth is about the structure of reality, you're here, now, experiencing this moment. That's enough. That's everything. Thank you for joining this exploration of the multiverse. May your dreams be filled with infinite possibilities, branching paths, and parallel worlds. May you wake refreshed, with a renewed sense of wonder at the vast, strange, beautiful reality we inhabit. Sleep well, traveler. In this universe or any other, consciousness is precious. Your consciousness, here and now, is a gift. Treasure it, use it, wonder with it. Until we meet again, in this branch of reality, or perhaps another, good night. And remember, in the grand multiverse of possibility, every question we ask brings us closer to understanding not just what exists, but what it means to exist. Sweet dreams, dear listener. May the infinite cosmos cradle you gently as you rest. The journey continues, always, in ways we can barely imagine. And that's the most wonderful thing of all.